People have been fascinated for centuries with the way our muscles act to generate movement. Anatomically, we know that muscles can induce movement at a joint by pulling on tendons that are attached to the skeleton. Simple enough, right? But the human body contains hundreds of muscles and joints, and understanding how all of these muscle forces work together to produce such an incredible range of movements is a tall order. So what can we learn about the magnitude and timing of these muscle forces? In many engineering applications, forces are measured using sensors that track how the material deforms when force is applied. Applying the same technique to human tendons is possible, but it requires surgical implantation. More commonly, computer models are used to estimate the muscle forces needed to produce joint movements during tasks like human walking. But many different muscles contribute to movement at any given joint, and computer models can't tell you for sure which combination of internal muscle forces is producing an observed movement. Given the limitations of surgical implants on the one hand and computer models on the other, we need a better solution. So we've been investigating a different approach that takes advantage of how waves propagate in tissues. Here's how it works. Inside a piano, if you pull a string tighter, the sound waves that you hear when you pluck it will increase in pitch. That's because the speed of the wave traveling along the string increases as you apply more force. These relationships are described by a few relatively simple equations. The wave speed, and thus the frequency, is proportional to the tension or force applied to the string. Our tendons are much thicker and created from a much more complex material than a piano string, so things get a little more complicated. When calculating the propagation speed of a shear wave, we have to think both about the tensile stress acting on a cross-section, and we also need to consider how tendon tissue responds to shear stresses acting within it. Because of this, the assumption that tendon will behave like a string is generally not a good one. But as you increase the tension, the two act more and more alike. That's because tendon tissue is made up of bundles of fibers that can slide relative to each other. This leads to a low shear stiffness, which allows us to leave that term out of our wave speed equation when the tendon is undergoing loading, as it does during movement. This results in a simpler expression. That means that we might be able to find the stress within a tendon by measuring the speed of a wave traveling along it. We decided to test this theory in the lab. In this setup, the machine applies a specific tensile load to the tendon. Then, a tapping device at one end starts a wave that travels to the other and is tracked using an ultrasound transducer. Looking at the measured wave speeds over a range of stresses, we can test whether our equation holds true. And it does. The data points fall exactly where they were predicted to. Now that we know the theory holds, we really want to understand how this would work for measuring tendon tension in real live people. For that, we created a surprisingly simple device. It includes a mechanical gadget that lightly taps the tendon 50 times per second. Each tap initiates a wave in the tendon, and 2 miniature accelerometers are used to determine how quickly it travels. As tendon tension increases, the time it takes for the wave to get from one accelerometer to the next decreases. The wave travels faster. In the Achilles tendon, we've measured shear wave speeds upwards of 100 meters per second when the person is using their calf muscles to push off from the ground. We've also used this device to measure forces on other tendons like the patellar and hamstring tendons. And in each case, we can measure what happens in the tendon when a person modifies their gait, for example, changing their step length or their speed. With this device, we can measure tendon forces in real, living, moving people in real time. But what is that good for? Millions of people around the world suffer from an impaired ability to move due to neurological disorders, musculoskeletal diseases, and injuries. The better we can assess how muscles behave in these conditions, the better chance we'll have to effectively diagnose the causes of movement disorders, plan orthopedic surgeries, design prosthetic devices, and prescribe therapies to help those in need. Someday, hopefully soon, we'll understand a great deal more about how our muscles do what they do, and this research is one step in that direction.